learning target for this lesson is to calculate derivatives of power functions, and I'd like to guide you to a discovery the mathematicians made about the general derivative formula, in that when they applied it, they started to see patterns in the derivatives that they were getting for power functions. And math is all about patterns, right? Especially calculus. So I want you to think back to, we used in our last lesson the general derivative formula to find the derivative of our parabola x squared. And you might remember that the derivative for all x is 2x. What I'd like to do now is look at the next highest power function, which is x cubed, and apply the general formula for derivative one more time. And I think just using those two examples of x squared and x cubed, you'll be able to detect the pattern, and we'll use it as a shortcut from here on out. So let's apply that general definition. So we carry our limit statement over, and I was careful to make this an h and not let it magically turn to an x like in our last video. But in our numerator, we're going to have the function of x plus h. So we take that quantity x plus h, and we substitute it for x in that function, so it gives us x plus h cubed, and then minus the function f of x, which is x cubed, all over our denominator of just h. We don't have to cube binomials as often as we have to square them, so you would write x plus h 3 times, you'd square 2 of them, and then distribute in the other x plus h. Or you can save time and energy and just trust me, I've got it here. That simplifies to x cubed plus 3x squared h plus 3x h squared plus h cubed. And then we remember to bring along our minus x cubed. And we can see right away, as usual, we've got some nice simplification that's going to happen here. That positive x cubed minus x cubed will cancel, and it looks like I can factor an h out of my numerator. When I factor the h out of the numerator, I'm left with 3x squared plus 3xh plus h squared, and that will now cancel with the monomial of h on the bottom, and we're ready to evaluate our limit as h goes to 0. When we substitute 0 in for both the h's that we see in that expression, we end up with just the one term left of 3x squared. So the general derivative of x cubed power function is 3x squared. So I'd like us to work out that one last example for a couple of reasons. The first is I want you to hopefully appreciate how wonderful and beautiful this formula is, and that it always ends up canceling and reducing perfectly to give us the derivative. And also to appreciate the fact that this is not a formula we would want to use for the next 9 or 10 months in AP Calculus. If we can find a pattern and a shortcut, I think we'd all agree that's the better route to go. So let's talk about that pattern or shortcut. Just to review, when we took the derivative of the power function x squared, we got 2x. And when we took the derivative of x cubed, we got 3x squared. So I'm hoping that you're seeing some movement, some changes, some repetitions on what happens maybe with the power, what happens with the coefficients. So based on just those two examples, I'd like you to make a guess or a hypothesis on what the derivative of the power function x to the 4th would be. If you happen to guess 4x cubed, you were correct. If you didn't see that, that's okay. Let's talk about what pattern exists and why it holds true for all three of those examples. If we look at x squared having a derivative of 2x, you'll notice that the power 2 became the coefficient in the derivative function. And also the 2 didn't just move, it actually was subtracted or lessened by 1. And the same pattern happens with the x cubed function. The 3 power becomes the coefficient 3 in the derivative, and we are going to take away 1 from the power of 3 to give us 2. So let's apply that one more time to x to the 4th. The 4 comes down to be our coefficient. We subtract 1 from the power, and that gives us 4x cubed. So now that we recognize and are getting comfortable with this pattern, let's come up with a general rule, and we'll call it the power rule, for any power function x to n, and n represents any power. Our first step was to recognize that the power becomes the coefficient. So the derivative of f will have a coefficient of the n power, and that's going to be multiplied by the same base x to the original power subtracted 1, so 1 less than the original power. So the formula, or the power rule for derivatives, is n times x to the n minus 1, and that does work for any power. And we're going to see in our examples that we have not just positive powers, but we have a lot of different types of powers to be able to deal with. So it makes sense the first type of power we'll look at is the first power, and it's a little more unique than just a power of square, cubed, or fourth, because something different happens with the exponent as far as when you are writing your new exponent. Let me just go ahead and start the example and show you. So we know that there is a first power here, even though it's not written. As mathematicians, we understand that there is a first power implied. So following the power rule, that first power will come down to be its coefficient. And the second step of the power rule says take that original power and subtract 1. That's what makes the first power a little bit unique, in that the power becomes 0. Well, we know that anything to the 0 power is actually just 1. So the derivative of x to the first power is actually 1. And that's unique because the variable actually goes away because it's to the 0 power. Speaking of the 0 power, that's actually our next type of example. So we're going to say that we have a function equal to c, where c is any constant, so a positive or negative number. And again, it's not written, but it's mathematically correct to assume that we have a variable to the 0 power there. So there are no variables present or visible, but we can always write that in because that is mathematically correct. So when we start thinking about the derivative, applying the power rule, we know the power comes down and becomes the coefficient. Well, the c acts as a coefficient, our constant, but we know that 0 times any constant is going to give us 0. That gives us a base of x to 0 subtract 1 is to a negative 1 power, which really none of that matters because that coefficient of 0 wipes out everything, variables and constants, and you end up with the answer for the derivative is equal to 0. So what that means is anytime you take the derivative of a constant function, the derivative is always going to be 0. And that's because there are no variables there to begin with. So the power of 0 wipes everything out, and you just get 0. We're going to see that so often, and it's such an important thing to know and know quickly that let's write that down. The derivative of any constant equals 0. And by constant, I mean a number that does not have a variable attached to it. And we know that derivative means slope. And so the slope of any constant function, which you remember is a horizontal line, is going to equal 0. So that's a nice graphical connection to what we're talking about here. Let's look at a power function that has a negative power to begin with. Not to worry, we're still going to follow the same steps. So your derivative will start with the power coming down to be the coefficient, which happens to be a negative 1. Just be a little bit careful with negative powers. When we go to subtract them, if we do it too fast, we subtract in the wrong direction, or maybe we add it, is what I'm trying to say. But if you have negative 1 and you take away a 1, you of course get negative 2. And through our knowledge of negative exponents, another way to write that derivative would be to keep the negative coefficient in the numerator, and to make that negative 2 power into a positive power, it moves that base of x squared into the denominator. We're going to see a lot of rational power functions in calculus. So I wanted to remind you that when you see a square root or cube root or any kind of root, it's actually a base to a rational power or a fraction exponent. So this is x to the 1/2. And the nice thing about the power rule is the steps are always the same. We just have to be a little more careful with them with certain functions versus others. So the 1/2 will come down to be the coefficient. I have to subtract 1 from 1/2, which will give me negative 1/2. And I'd like to practice rewriting this so that the negative power becomes positive. So the coefficient is already a fraction, so we've got 1/2, and then x to the 1/2 becomes positive in the denominator. You can also write it this way.